Alright, so I'm making this video because I wanted to make an easier explanation of backpropagation for feed-forward neural networks, because a lot of the explanations that I found online were either long or confusing with like weird notation or something, and I just wanted to make a very concise explanation for beginners or people who are very new to this kind of thing or have a limited mathematical background. So let's start by reviewing the structure of a neural network. Basically, we have the neurons here, the input neurons, or actually this could be any neurons within the layers. We just took a random cross section of the network. So this is 3 neurons here, 4 neurons here, or 3 neurons here, and we have the connections, the weights in green here, and the weights in red here. So I actually denoted this layer L for the last layer. I'm gonna call it L for last layer. And so this is where we get our outputs right here. And this is L minus 1, which is the layer behind that. This is L minus 2, the layer behind that, and so on. So what we're going to look at here is a notation for the weights that will help us in the future. So I'm going to call these weights here WL minus 1, and then I'm going to call these weights here, oops, that's orange. These weights here WL minus, or just WL, right? So the weights behind layer L are WL, and behind layer L minus 1 are WL minus 1. And the way we're actually going to denote these weights in matrix notation is we're going to make a matrix L minus 1, and we're going to have it dimension 3 by 4 for this specific example right here. Because we have 3 neurons feeding into 4 neurons. So we're going to have a 3 by 4 matrix, right? And then it's going to look like this. All right. The 1, 1 position is going to be the neuron that connects the first neuron here to the second neuron in the next layer. Or I mean, the first neuron in the current layer to the first neuron in the next layer. So it's 1, 1. This is W1, 1. W1, 1. And then W1, 2, I don't know if you're following, it's going to be the first layer in L, or the first neuron in L minus 2 connected to the second neuron in L minus 1. So this is right here is going to be W1, 2. All right. So to practice this, I'm going to do a very quick example and just to clarify a little bit. All right. So let's draw another network here. We're going to make this 3, and then we're going to have a. Actually, let's make it 2 by 3 here. All right. So we're going to call this the neuron we're talking about here is going to be the ith neuron, and this is somewhere in here is going to be the jth neuron. That's just our indice notation right now. So let's say we wanted to denote the layer, or we're going to call this layer L here, layer L minus 1. Let's say we wanted to denote this connection in particular, the one that brings the second neuron in layer L minus 1 to the second neuron in layer L. Well, the way we would denote this matrix, or the way we would denote this weight would be WL, right? So this weight matrix, this blob of weights here, and then we're going to specify 2 to 2. Okay, that represents this one. And then if I wanted to have a connection going from the second neuron in L minus 1 to the third neuron in L minus 3, or in L, then we would have W2, 3. Okay? Of course, layer L. So that's how that works. And now that we have that notation, we're going to define the inputs, right? So I'm going to draw this in here really quickly. So if we want to find the value being inputted into, let's say, a neuron in layer L, and we're going to call this the jth neuron, right here, then what we would have to do is we'd have to take the sum, right, the sum of k, which is the number of neurons here. So the sum over, let's call that I, just to clear things up a little bit. So I, the sum over all the neurons here, times time, we're going to have to take the sum of all these neurons, right? Each of these neurons, we're going to have to multiply its output value times its weight going to here, and we're going to have to sum these all up. And then finally, we add the bias. which is how much it's shifted over here. So the way this is going to work is we're going to put a W here. So the weight's in this layer, and it's going from I to J, right? It's going from I, each of these I's, to the singular J here. So WLIJ times the outputs, and we're gonna the outputs of this layer here. We're gonna label this A for activations, but they're basically the outputs. So AL minus 1 of I, right? Because we're summing over each one of these, and then we're going to add the bias for J. Okay, so this makes sense because as neural networks work, they iterate over each neuron in the previous layer and each layer in the next layer, each neuron in the next layer to get all the output values. And we define that recursively. We're going to keep going through each layer and layer, feeding the values forward. So the way we get this value, the output value, is we simply apply our activation function, which I'm going to call lowercase sigma. We simply apply our activation function to each input. So what does that mean? That means that if we wanted to calculate the next layer, right, layer ZL plus 1 J, we would simply use the sum, sorry, I should redo this, the sum of all the neurons in that layer plus WIJL plus 1 times this stuff, all this stuff right here. I'm going to change colors. All this stuff, right? Oops. This. And I'm going to plug that into the sigmoid function here. ZLJ. Right? So that's how this recursion works, basically. All right, so that seems simple enough, right? Although it is a little confusing because of all these I's and J's and all this crazy indice notation we have here. So I'm going to clean this up a little bit by bringing in matrices, all right? So instead of doing singular indices and iterating over all of the neurons, we're going to just do one quick, clean matrix operation. Okay, so how is this going to work? Well, we're going to define a column vector ZL, right? So a column vector for layer L, and that's going to include all of the inputs for that layer. So ZL, ZL2, dot, 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 ZLJ. All right, so that seems simple enough. So the way this is going to work out is, I'll explain each part of this in a second, but it's going to be the inputs for layer L are going to be the transpose of the weight matrix for that layer times the activations for the previous layer, the column vector of activations for the previous layer, plus the biases for the current layer. Okay. So this actually looks pretty similar to our sigma notation here. We have a lot of the same components, except the summation is replaced by matrices. And the reason why this has to be transposed is, let's take a look at the actual weight matrix right now, the transposed weight matrix, okay? W11, W12, W13, dot, 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 because remember we transposed it, so W21, W31, dot, 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 dot. Okay. Now, let's draw the activations of the previous layer, or the outputs, as I like to refer to them. So A1, A2, dot, dot, dot. All right. So what happens when we matrix multiply? Well, each element here, the corresponding elements get multiplied and summed together. So this element right here is going to be multiplied with this one, right? W11, A1, L minus 1. And then that's going to be added to, let's change colors again, W12 times A minus 2, W21, WA2L minus 1, right? And then that's going to continue on for a while until we've successfully multiplied this first little row and column, right? Or this first row by the next matrix. So this is going to be the first element of our new matrix, right? This is going to go in here. And then the same thing is going to happen for here, and then for here, and here, and here, and here, everything's going to fill up here. So let's just take a look at the first element, okay? We have W11 times, or sorry, I need to put the L in here. L, and then the L for here. Okay. So we have WL11 times AL minus 1, 1, plus WL21 times AL minus 1, 2, dot, 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 dot. So let's draw a neural network again, just to visualize it. So let's see. Let's call this layer L minus 1. So this matrix right here, this blue one, is our activation matrix, right? So we're looking for the inputs. Or this is our input matrix. We're looking for the inputs to layer L. So weight 1, 1 is right here. Activation 1, L minus 1 is this output here. So we multiply these together, put them in here, and we add them to 2, 1 times AL1, A2. So 2, 1 is here, and AL1 is 2. So as you can see, the matrix multiplication is actually iterating over all these neurons and multiplying their activations by their corresponding weights, and then putting that in the first element of the input matrix. So really, with this nice matrix operation, we have shortened our notation here. Okay, so that's good, because now we have a much easier way of looking at things. And also, we can do a little bit more simplification by saying that the activations for layer L is just the activation function times the L, right? Or the activation function of the vector. And we're going to have to specify really quickly what this notation means, because this isn't a very natural thing. This is just simply the element-wise activation of everything, like this, as so. All right, dot, dot, dot. So now that we have all these equations cleared up, we are ready to start the real work, okay? And I will come back in just a second, because I'm going to clean up everything a little bit and write down the equations. So see you in a second. Okay, we're back. So these are all the equations we derived earlier, and we're about to put them to use, except since we're doing supervised training on the neural network, we want to have some sort of way to grade its performance, and that's going to be with a cost function. So we could really do the cost function as anything we wanted to, but I'm going to pick a very easy example because it just plays out nicely in the end, and you'll see why. But we're going to define the cost function as 1/2 of the sum of the expected outputs, okay? The expected outputs of the final layer minus the actual outputs of the final layer. Then we're going to square this. Okay, so the reason why we're doing this is we want the performance of the neural network for each example to reflect the outputs of each neuron at the end, right? So this is the output we want, YLI, and this is the output we actually get. Okay, so now that we have that established, let's take a look at what it would look like. And unfortunately, since we live in 3 dimensions, I don't know if that's unfortunate actually, that's probably good, but since we live in 3 dimensions, I can't show you what it looks like because this is a multi-dimensional data set, and it's very difficult to draw a multi-dimensional data set. So I'm just going to pretend like we have two pieces of data and draw it as a parabola. And turns out, as you generalize into higher dimensions, this little cup shape stays the same. So the goal is to get the cost as small as possible, which is, I guess you could kind of think of as the error. We want to get that cost as small as possible. And the way we're going to do that is we're actually going to follow the gradient backwards. And if you're in single variable calculus right now, don't worry about gradients. It's basically three-dimensional generalization of a tangent vector. I mean, that's kind of what it is. It's enough. That's a sufficient definition for what we're doing right now. But we're essentially just going down to find the local minimum. So we can actually just go in and do it right now. Let's talk about it. So here's our cost function, and the way we're going to do this is we're going to take the partial derivatives of the cost function with respect to the outputs, right? The outputs of the last layer. Let's just take a look at the last layer as an isolated example. So we're going to define this quantity, this partial derivative, as delta j capital L, right? And we're going to more generally, we're going to say that the change in the cost function with respect to the change in, or the way the cost function changes based on the way that the inputs in layer L change are going to be the delta values, lowercase delta values, for this specific layer and the specific neuron. All right, so what exactly is a delta? What exactly are these delta values, these mysterious delta values that we're referring to right now? Well, they're quantities that we could use to change the value of the neuron. Like, they're quantities that, if used to change the actual input value of the neuron, that's how we're calculating how those changes would affect neurons down the line, right? So if this is layer L and this is neuron J, if I add to the input delta Lj, how is this going to change all the neurons down the line? Well, it's going to affect these ones. It's going to affect everything else down the line, because since these ones are all affected, all the preceding neurons, or all the next neurons, are going to be affected too, because they're all interconnected. So if you're really good at calculus right now, you're probably seeing that this is one huge chain rule problem. Right? This is an absolutely massive chain rule problem because it's a function of tons of neurons. But we're going to simplify it a little bit, actually, because one smart guy, or probably a few smart guys, noticed that we can calculate these delta values for the final layer and propagate them backwards, which is where the name of the algorithm comes from, backpropagation. We can propagate the error in the last layer, or the delta value in the last layer, propagate it backwards and use them to calculate the errors in the previous layers. And I'll show you what I mean in a second. So let's first work out, from a purely mathematical standpoint, let's work out what this partial derivative for the last layer is. Using the chain rule, for partial derivatives, we can figure out that this is the rate of change of the cost function with respect to ALJ times the rate of change of the ALJ with respect to ZLJ. Okay? All right, so what is the rate of change with respect to ALJ of the cost function? Well, let's go back up and look. All right, well, we simply need to take the partial derivative. I say simply right now, but it may look pretty complicated because of the sigma right here. We want to take the partial derivative of this with respect to ALJ. All right, so let's think about what we're doing when we're taking a partial derivative. We're keeping every other variable constant except for the one that we're taking a partial derivative for. So if we're taking the partial derivative for ALJ, that means nothing else is going to matter except for ALJ. So since we're summing over I, the only time this quantity here is going to be non-zero is when I equals j, or else it'd just be a constant term, because changing ALJ wouldn't do anything to a term that doesn't have ALJ in it. So the summation turns out to be, this partial derivative actually turns out to be really easy because the summation is removed. So now this simply turns into, bring the 2 down here, so that's going to be blah blah blah. It's just going to be AIL or AJL minus YJL, right? Because of the chain rule. You should do this derivative by hand for practice, but that's just what it is. All right. So now we're looking at how the activation function changes based on the inputs it's given. Well, that's easy too, because we know that the activation function of JL is just equal to the activation, or the activations of ALJ is just equal to the activation function with ZLJ as inputs. So partial ALJ, partial ZLJ is simply the derivative of the activation function. So that's easy. We're going to call that sigma prime ZLJ. Okay, so let's scroll down a little bit. So now what have we done? Well, we've calculated the delta for the last layer. All right, delta J. And as we said earlier, that's equal to ALJ minus YLJ times the derivative of the activation function, CJL. And this is really convenient because this is an extremely easy value for us to calculate. We just take the output value minus the expected output value and multiply that by the derivative of the activation function. That's very easy. It's quick computation. Okay, so now our goal here is to generalize this function. All right, we're going to generalize this partial derivative to delta. So delta L of J, remember we're trying to generalize it, would be delta of Z, lowercase l, because this is any layer, J. Okay, so this is where things get notably more complicated, because now we have to observe that in the last layer, changing a single neuron only affected the output directly, because it doesn't feed into anything; it just feeds directly into the output. So changing a neuron in the last layer wasn't going to do much. But if we change a neuron in an arbitrary layer L, lowercase l, let's just say we change this one right here. Sure, it only affects this one, but then it's going to affect all the ones down the line and all the ones that those connect to and all the ones that those connect to, and it just gets very messy. So how are we going to fix this? Well, okay, actually, sorry, I misspoke a little bit. It actually affects all of these. And then down the line, those affect those, blah, 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 blah. Whatever. The point is still the same. What we should do instead is we should look at how the changes in the next layer, L plus 1, affect the cost. So we're kind of like, I mean, this is kind of a very figurative way to think about it, but I guess you could say we're kind of procrastinating our work. Like we're saying, oh, we want to calculate how the cost function changes with this layer. Let's just put it in terms of the next layer, and then the next layer, and then the next layer, and the next layer. Except we're doing this backwards, so it's not procrastinating, I guess. So, all right, that's easy enough. We can see that we're gonna try to put that into terms of the next layer. Actually, I don't think I'm gonna have enough space because this is a very big equation, so we're gonna continue down here. Okay. So, how this neuron affects the cost function should be a function of how all the neurons, the sum of all the neurons in the next layer, of how they affect the cost function, right? So it's going to be sum of this cost function of L plus 1 over K, right? And I'm going to denote K as the number of neurons in this layer, right? Times, since we're using the chain rule, how these neurons are affected by the previous layer. All right. Now let's go over again why this makes sense. What are we doing in this sum here? Well, we're looking at how this term right here, this partial derivative here, expresses how this neuron will affect these ones, and then this term right here expresses how these neurons, which were just affected by the red, are going to affect the cost. So really, this makes perfect intuitive sense, really. So now let's analyze this a little bit further. Okay. What is this green expression here? Well, if we look back, this is just delta, because we defined earlier. We defined, let me see where it is. We defined delta as the change with the change of the cost function with respect to a specific neuron ZLJ. And here we have the change of the cost function with respect to a specific neuron ZL plus 1 ZL plus 1K. So we can rewrite this entire expression as, oops, that's a really ugly sigma. Hold on, I'm going to fix that. That is another one. Okay, whatever, I can't make a perfect sigma right now. That's just going to be delta L plus 1 K. And then the red we're going to have to do a little bit more manipulation here, okay? We have to look at how this is going to affect each layer. So let's take a look at this. All right. I want to examine this in a little bit of a separate area right now because the examination can get pretty lengthy. And we'll come back to this in a second. We'll come back to this part in a second. Just know that we have to put something here. All right. So let's go off to the side and examine this. So let's look at, I'm going to change back to white. Okay, let's look at ZL plus 1 really quickly, K. Let's look at what that is. So from our previous definitions, I'm going to rewrite the equation for the activation in a certain layer J. So we define this as the sum of all the previous neurons. Sorry, I keep saying activation, the input here. We define this as all the previous weights of the layer times the previous activation layer times J plus the biases of layer. Oops, this should be 9. The biases of this layer, right? So let's translate that really quickly. Let's translate that into our current indice notation. I know I said I was going to use matrix notation, but that's going to come soon. We just have to trudge through this horrible indice notation really quickly. I say it's horrible, but it's good. It's very good. We're just over-exaggerating a little bit. Okay. Ik of L plus 1 times AI L plus BJ, or sorry, BK, my bad, BK of L plus 1. Okay, so this looks simple enough so far. We just translated, this into this, right? Now we need to go about taking the partial derivative, which is what we're looking for, with respect to the activations in the previous layer. Okay. Oh, sorry, this should be a J. Okay. Now we can actually do a little bit of substitution here, because this ALI, or this ALI, is really the sigma, the activation function of ZLI, right? So let's take a look at this right now. So we already know that this bias is going to disappear because it's a constant term, and the derivative of any constant, no matter what, is going to be 0. Okay? And now we need to take the derivative of this function right here, just this part. All right? And let's look at the only terms that contain ZLJ. We know that this is a summation over all of the previous neurons. And we're going to do a similar thing that we did in getting the derivative of the cost function. And we're going to notice that this derivative is only has a non-zero value when I equals j, right? So really, we're just taking the derivative of wjk L plus 1 times ajl. And the derivative of ajl because wjk is a constant, the derivative of ajl is simply wjk l plus 1 times the derivative of the activation function times zli. Okay. So that's easy enough. We've calculated this seemingly difficult partial derivative, and now we can go all the way back and plug it into here. All right? Let's do that. W I K, or wait, am I using J or I? I don't remember. I think we're using J, right? Yeah. W J K of L plus 1 times the derivative of the activation function of Z L J. Okay? All right. Let's double check I got that right. I'm a little bit paranoid here. Oh yeah, sorry. I should have changed this to a J here. My bad. Okay. So all we need to do is calculate that over all of these K, and then we'll get our delta value here. And now we can do this for every single layer, propagating this delta error back, right? So let's actually come back to this in a little bit, but first I want to turn this into a matrix notation. Okay. Okay, I cut away for a little bit, but we're going to rewrite that equation that we just made. All right, zk delta k, the delta of the next layer times wjk l plus 1 times the derivative of the activation function, sigma, lowercase sigma, of course. Oops, I like that. Okay. Z, J, L. Okay, let's transform this a little bit. And you should recognize something, or you should see a little bit of a correlation between something we wrote down a little earlier and this equation here. All right. Now, let's note something really quickly. The only things being affected by the summation is this expression right here. Nothing else is changing because this is being kept constant right here. This is just being multiplied by each element individually. All right. So if you notice something, this expression here, remember we're solving for J, looks a lot like the expression for ZLJ, which is a matrix multiplication. And I'm going to remind myself really quickly of what it looks like. So ZLJ was just the iteration over all the neurons in the previous layer of like this, like so, like this. L plus 1 times AJ L. Let's get rid of this actually. Yeah, let's go back and get rid of that because I want to keep this kind of consistent. Times AL minus 1 J plus BJL. All right. Sorry, this should be an I. Plus BJL. Okay, and we remember that the matrix form of this was simply the transpose of the weight matrix times the activation matrix plus the bias matrix. So let's extend that principle, everything that we did here, and we're going to extend it to the equation for the delta value in layer L that we just got, and we can transform this. Now, if you notice, pay close attention, and you'll see that in this equation, I is changing, and it's on the left spot, but K is changing, and it's on the right spot here. So we actually need to take the transpose of the transpose, which is simply the regular matrix. So if we want a matrix of deltas in layer L, we simply have to do the weight matrix, the normal weight matrix, not the transpose, L plus 1, times the deltas, the vector form of the deltas in the next layer, and then we need to multiply it element-wise by the activations, right, the derivatives of the activations in the current layer that we're looking at. Okay, and I want to be 100% clear on the element-wise multiplication, because if you mess this part up, your algorithm is not going to work at all. Okay, let's define element-wise matrix multiplication again, or element-wise vector multiplication. So we're going to do this really quickly because this might be reviewed to a lot of people. I'm not sure. Let's say we have a matrix 1, 2, 1, 3, 0, or something, and we want to do the element-wise multiplication of 0, 1, 0, 0, 5, or something. Then we're going to take 1 times 0, which is 0, 2 times 1, which is 2, 1 times 0, 0, 3 times 0, 0, 0 times 5, 0. Wow, I was really lazy with this, wasn't I? Whatever. You get the point. You just multiply each corresponding element here, and then that's your new matrix. So I encourage you to take a look at this and see how this matrix multiplication actually works. Okay. So this is really great, because what we've done is we've defined a way to get delta L, right? The vector, or the matrix representation of all the deltas in layer L, right? Based on the deltas in the next layer, right? So if we want to make this algorithm work, if we want to solve for all the deltas, we first have to solve for delta capital L, right? And we've already done that. We solved for delta capital L a while ago. Let me see if I can find it. It's right here. It's right here. This is delta capital L. And so we simply plug this in for delta capital L minus 1, and we will be able to solve for all the delta L's. Okay, and you might be saying, okay, well, that's great. Now we know how each little change on each neuron affects the cost function, but how do we adjust the weights like that? Well, we have to use the chain rule again, except let me find some space real quickly. We're going to look at how, finally, we're getting to where we want to be. We're going to look at how a change on weight ij affects the cost function. So let's just do some expansion with the chain rule. We can rewrite this as the change in the result of z lj, right, times delta z lj based on weight wij. So we're finally going to get to the point where we can actually figure out how a change in WLij changes the cost function. So we can expand this using the chain rule by looking at how the cost function is affected by input zlj times the way that the cost function is, or the way that zlj is affected by WLij. So first off, you should notice right away, or maybe not right away, but you should notice eventually that this quantity is simply delta Lj. I'm going to draw this a little bit neater because that's what I like. Delta Lj, right? And we calculated that earlier, so we know this already. And then figuring out this quantity right here is going to take a little bit of thinking, but we'll get there. So let's actually take a look at what's happening in this neural network. I'm going to draw this again for like the whateverth time that I've done it. Well, so we want to look at how, let's call this L, let's call this one L minus 1. We want to look at how the activation in J, let's just pick a random one. This one's J, okay? I like this one, it's called J. We want to look at how weight ij, let's just say let's call this one I, because I've already drawn it. We want to look at how weight ij affects z lj, right? Now, let's say something like we're going to call something like a partial sum, all right? And the partial sum is going to be this stuff from these two weights right here. Let me draw this. These two weights, right? The ones I highlight in red here. These two weights times their respective activations, right? That's just going to be, let's call this like S or something, right? S. So ZLJ is dependent on S plus A L minus 1 J, or sorry, L minus 1 I times Wij L, right? Because this weight here going from I to J times the activation at J, which is like the output, so A L minus 1 J, or this is I, sorry, this is A L minus 1 I, multiplying these two is going to give you part of ZJL, plus the other half, which is, or the other parts of it, which is S. So taking the partial of this with respect to Wij is easy. It's just 0 plus A L minus 1 I. This just becomes 1, so times 1 here. Oops. This just becomes 1. So now we've completed this. We know that. Yeah, let's call this. I kind of want to make it green. I like green. So we know that this is going to turn into AI L minus 1 times 1. But let's just get rid of that. So, and there we go. We've completed this. A change to the ijth weight is going to result in, or the rate of change between the cost with respect to weight Wijl is just the delta value that we calculated earlier. Delta Lj times times A L minus 1 I. And that's really easy because we have all these numbers calculated beforehand. And what would make this operation even easier is if we change this into matrix notation, so we could do this very quickly and swiftly. I guess if you want to talk about it that way. If we could do this in one very quick matrix multiplication operation, then we could speed up our software by a lot. So we're going to do that right now. Okay. So I'm just going to write out what it turns into and explain it after I have written it. So, partial with respect to the weights in this layer. Okay. This is going to be A L minus 1 times the transpose of this. All right, now let's look at why this is true. We're going to, which we should, if we do this right, we should get the correct dimensions for the weight matrix. So, all right, so this is A L minus 1 1, A L minus 2 2, or sorry, L minus, I keep messing that up. A L minus 1 3 dot dot dot, and this is going to be delta L1 delta L2 dot 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 delta whatever dot. I kind of actually like making this 3 elements here. 3 dot dot dot. So what happens in the product matrix? Well, it's going to have this dimension here by this dimension here. All right, let's change colors again, make it more clear. The dimensions of the product matrix are simply going to be this, which will be right here, And then this is going to be right here. Let's check if that's correct, right? So how do we matrix multiply? Well, we're going to multiply this element by this element, and that's going to be right here. So AL1 1 delta L1, and then we're going to take the next one, so it's going to be comma AL minus 1 1 delta 2L dot dot dot, right? So really, this first row here, right, which is going to be ij, W11 is going to be A11 delta 1, or AL minus 1 1 times delta L minus 1, which is exactly what we would see in our formula here. But I mean, okay, you might be saying, well, that could be a simple mix-up because the j and I are equal here. So let's calculate W21 or W23. Okay, so W23 is going to be here. 1 2, right? So 1 2 1 2 3 should be right here, and that's going to be A2 L minus 1 times delta L3. And so we have exactly what we expect here. So we can get the entire weight matrix for one layer in just a single matrix operation, which is extremely efficient compared to the probably millions or billions of operations you'd have to do if you were doing this without matrix multiplication. And there are libraries like cuBLAS or all these different linear algebra libraries that will do this kind of multiplication extremely quickly. Okay, so you may think we're done. You might look at this and say, okay, well, we know how to calculate the deltas. We know how to calculate the weight matrix with respect to the, we know how to calculate the partial cost matrix and everything, blah, 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 blah. So now we're done. We just have to perform all these operations. Well, that's wrong because we still haven't figured out the biases yet. And the bias is going to be very simple. We're just going to use the chain rule again. Let's get some nice space here. And let's do this in blue, because I like blue. We haven't used blue in a while. Okay. So we want to figure out how the cost function changes with respect. Let's take a lighter blue. The cost matrix changes with respect to a bias. We'll call bias Lj, right? So we're going to use a chain rule again. It's going to be with how the cost changes with respect to the Lj. Notice anything, by the way? And then times the Lj with respect to weight Ij. Okay. Oh, sorry, not weight Ij. I'm getting a little confused. BLJ. Okay, so let's look at this thing again. What is this? Well, that's easy. I'm going to circle this around. What is this? That's easy. That's just delta Lj, right? And then now we have to always do this over and over again. We have to go back here and look at the more complicated part. Well, let's use green, by the way. This part. All right. So we have our old equation for activation, which is ZLJ is equal to the sigma over I of, man, I'm getting tired of writing this. This times AL minus 1, I plus BJL. And well, you might say, oh great, we have to do another partial over this whole summation. We have to think hard. Well, not quite, because we're taking the partial of this, or we're taking the partial of ZLJ with respect to the biases, bias J, and since bias is nowhere within this part, this just becomes 0. So it's going to be 0 plus the derivative of BJ, or BLJ with respect to BLJ, which is just 1. So now we just multiply this by 1, and as surprising as it seems, or maybe not surprising if you're like a math genius or something, the change in cost function with respect to bias Lj is just delta Lj. It's that easy. And then expanding that to matrix notation is trivial because it's just, because it just becomes the change in cost with respect to bias for the bias vector L is just the delta vector L. And we're done. We're done with backpropagation. All right, so these are our equations we've derived. I've boxed them because I like boxing things, and well, that was great. We've successfully derived the equations for backpropagation in a simple feed-forward neural network in terms of matrix operations, which are very efficient using certain libraries that you can download. And yeah, I hope you understand everything. If you have any questions, leave them in the comment section. I will try to get back to them as quickly as possible.